Right, so I'm Chris Seaton. I'm going to talk about Truffle startup, Warmup, and some challenges and opportunities. I'll start giving some context. There's 50 people in this meetup, which is fantastic because of every other time we've done it, it's been a smaller number, a physical conference. So it's great to speak to more people, but I'll give a bit of background, a bit of context about what I'm working on and why I'm looking at startup and Warmup and things like that to start with. So I work at Shopify. May not have heard of Shopify. It's a large Canadian e-commerce company, but when we run people's stores, we let them brand them themselves. So you may not know about Shopify unless you're in that space. But we are fairly large. I think we're now the largest company in Canada. We've got over 5,000 employees. We've got 1 million plus merchants, so people selling on top of our platform. Working in 175 countries. This makes us a large, complicated operation, a large, complicated application that we're trying to run. So we've got over 3 million lines of code. We're averaging 5 million requests per minute. And that peaks up to 170,000 requests per second. And we ship 40 new versions of Shopify also about each day. And that's why Warmup and Startup is important, because if we can't start the application and then leave it running to start or to warm up for a very long time, because 40 times a day there's a new version of the application coming out. I think that contrasts to some of the way people often see enterprise Java, and they think about starting a big application server and then letting it warm up for a day and then running it like they do in banks, but we wouldn't be able to do that. And all this engineering is running on a core on Ruby on Rails. So there's a core Rails monolith at the center of what we do. And that's got a fairly conventional Ruby and Rails architecture. So it runs on the standard version of Ruby at the moment. And if you knew Ruby and Rails, you'd recognize the application as being a modern Rails application. And what this does is it serves storefronts to customers. So people who go shopping for things, this is what they see. The innermost loop is rendering templates. So we render HTML from data about what's in the shop and how people want to style their shop, and we render that out to users. We've got an application called Storefront Renderer. This is the critical path of our application, the most important things. So serving a storefront to users who are browsing as quickly as possible. And this doesn't use Rails. We've extracted this out of our core monolith, and it uses the Ruby web server interface directly. So this is a slightly simpler Ruby application, and this gives a bit more freedom to experiment with how Ruby applications run and perform. There's a bit less dependencies, a bit less code, and it's this application that Truffle Ruby we're experimenting with running. And Truffle Ruby is an implementation of Ruby using the Truffle framework, which then, of course, uses Graal as well. Truffle Ruby is an Oracle project originally. There's a team at Shopify, and there's 4 people working on it at each company now, so 8 overall. So it is quite a large, important effort for Truffle. It's one of the original group of Truffle languages, so being developed since 2013. It aims to be drop-in replacement for standard Ruby, so it's not a different language. It's not aiming to do anything differently. It just runs Ruby better. It's got a few more functionality points like polyglots, but we're not using those at the moment. It's highly compatible according to Ruby specification tests. It supports unmodified C extensions using Sulong, and its performance on real code can be as much as 10x compared to the standard implementation of Ruby. So it manages to use Truffle effectively to achieve a really significant increase in performance on some real code. Again, for context, I'm talking this workshop about CE specifically, so the community edition of Graal, and the JVM edition I've used just to simplify, to show a few data points. But we are also testing EE and we are testing native, and these numbers are different on both these configurations. I'm mostly showing what Oracle's built here. So I'm doing a sort of community service of showing some points about startup and warmup, but a lot of the work here is really from Oracle and the people there. But I'm going to show how it applies to Shopify's code. My goal here is to talk about the current situation with warmup and startup on a large production Ruby application running on Truffle. I think at Shopify, we certainly have the largest Ruby application anyone's tried to run on Truffle. We probably have the largest Truffle application anyone's tried to run. So we can study this stuff at quite large scale. I want to show the impact of some options that you may already be aware of on our application, because it sort of scales it out. But also want to raise awareness of some options and patterns you may not be aware of, and sort of document that a bit, raise awareness of it, and invite some more discussion and ideas. So the current situation. It's important to know that the Truffle philosophy is of single representation of programs. So the big idea is that you have just one way, one set of logic for executing your application, and that includes in the interpreter and in all the different compilation tiers, when being debugged, when being introspected, when being profiled. There's only one representation. That's quite different to other VM implementations where there's often many different ways of doing it. But in Truffle, the idea is there's a single representation that the language implementer uses. The other Truffle philosophy that's really important is pervasive caching and profiling. The issue with the single representation means that everything you want to do at every tier has to be in there in that one single representation. And that's quite different to a normal VM implementation where there'll be very different ways of doing things in different tiers. So especially with the caching and profiling, almost every time we add an optimization for peak, it adds some interpreter overhead because it uses the same representation. And Truffle languages generally are very aggressive about profiling caching. They have quite a lot of profiling caching, and being able to add that is one of the strengths of Truffle. In Truffle, someone can add a new profiler or a new cache with almost no work, whereas in other systems that can be very, very complicated, and therefore people don't often add them. And Truffle Ruby is particularly extremely aggressive about profiling caching, and that's because of the very dynamic nature of Ruby and the way that the dynamic nature of Ruby is used idiomatically in Ruby applications. So people aren't afraid to use things that need a lot of profiling caching to optimize. That's how we managed to get this 10x speed up, by having a lot of that. But we can see the impact of this by using the option profiling equals true or false. This doesn't get rid of all profiling and caching in Truffle. It just removes some of the things such as branch profiling. It turns them into no ops. But the core to the no op is still there. So it's still a bit of an overhead. But we can see the impact that this makes. So I looked at for our application, I looked at the time to run the first request. So this is the time to boot the whole application and to service one request. When we run that with the interpreter with no profiling versus the interpreter with profiling, we can see the difference. So this is time to service the first request. So here, lower is better. So having profiling does add a significant interpreter overhead. And as I said, the disabling doesn't remove all of it, it just removes those bits which are easy to do disable. But then profiling does add a performance increase when you're running the compiler. So one of the situation starting points we have is there is an overhead from this profiling. And does that philosophy work with real applications? So if we're going to profile everything and have a single representation of everything, does that match what our applications actually look like? How many methods need any kind of profiling or caching at all? And there's a great deal of code in our application that runs only once. Because every top level scope in Ruby, so files, the top level of files, top level of classes, top level of modules, they often run only once. So why do we profile them? Why do we cache in them? Why do we build up logs of things that are never read? This is part of the Truffle philosophy of being this one way to do it, but that's the impact of it, that it impacts things which only run once. And the other point is there's always corner cases, right? So if we say things are probably only run once, I'm sure there's some cases where things are actually run lots of times, so we do need to optimize. So it's hard to get it right. And what problems does it cause? Of course, we get very long compilation queues running a production Truffle application, up to 4,000 queued methods. And I've seen similar or even a bit worse in some other languages. Like I've seen similar queue sizes in Truffle Squeak, for example. So having 4,000 methods queued is a lot of methods, I think, compared to other VMs I've looked at. There's also often a long delay for compilation. So on average, the delay for compilation in our application is 4,000 milliseconds, which again is a lot. Something could be waiting quite a long time to be compiled. So some of the observations, we'll start with the most basic options you can use to configure startup and warm up. So the compilation threshold, splitting and inlining. So that's for compilation threads later, sorry. Difference between splitting and inlining that makes, if you disable splitting, you can reduce the time needed to start and run your application. Obviously, this has an impact on peak performance, but disabling splitting means we can get into reasonably good compiled code reasonably quickly. And disabling inlining also reduces the time to get into reasonably good code reasonably quickly. There's also additional tweaks to inlining that you can use, such as you can have custom logic for deciding when to inline something or not. There's a trivial option, there's a none option, and there's a default. You can also decide how much, when you want to trigger inlining or when you want to restrict inlining based on the maximum sizes. And the same with splitting. You can configure based on what the callee looks like and what the caller looks like. So first option people may not be aware of, or if they are, they might want to see the impact of this on production application, is the engine mode. So there's an option engine mode, there's a default, there's a latency, and there's a throughput. So if we're talking about startup and warm up here, then we'll be looking towards the latency option probably. The idea is that gives you the quickest time to respond to something. Versus the throughput, which gives you the peak performance, which is often what we've been optimizing for in Truffle. So the throughput option gives us a startup time around 108, and the latency takes that down below 100. So that does have an impact on our application's boot time just by using this option mode, switching it to latency. How it does it? Well, the default and throughput option, all they really do actually is default and throughput enable splitting and inlining, which we already saw the impact of, and latency just disables splitting and inlining. And that's all they do. The documentation says that default balances between the two, but I think it's just the same as throughput really. But if you're running with an application that you want to start more quickly, then using latency and just switching on that option is a way to do it. So it's a macro option that enables things. A good pattern to know how to use it though is in Truffle, when we write languages, we write launchers that handle things like the arguments, and you can set options in these launchers for when you launch your application. So something that Truffle Ruby does is it looks at what application you're launching and uses that as a heuristic to decide what mode to use. So this is an option for improving starter warm-up that we don't need to defer to the end user. We can apply a sensible default for from our language rather than just at the Truffle level. So in this case, Ruby says that if the executable is gem is the package manager for Ruby, then it's fine for it to run with the latency mode because of that's likely to start and run fairly quickly, and it's the startup time that's important for installing a package or something like that. If we're running with Bundler, which is another sort of Ruby package manager, but it has an option to execute a full program. So what we've done is we've looked just not at the executable name, but also some of the options and parameters that's given to the application to decide what to do. So when you're thinking about these options, you don't need to think about them at just the Truffle level. You can think about them, you can think about what to do in your launcher to select the right options and improve things. Multi-tiering. So multi-tier became the default about 3 months ago, I think. You can still disable it by setting it to false, but you should have found it enabled in your Truffle languages since then. What it does, from what you can see, is you'll see your methods get compiled twice. They get compiled in a lower tier, and then they get compiled again if they still get hotter than that in a higher tier. This will have an impact on your queue, which we'll talk about later when we talk about compilation queuing. What it does is this has a pretty significant impact on startup time and time to first request. So if it was disabled, which was the previous default, we're up to around 125 second start, and enabling this gets us down to that 108. So this does have a very big impact on startup time, even though it's compiling more stuff because it compiles stuff twice. How does it do it? It has a separate lower threshold for the first tier, the lower tier, and there's several options to configure what that threshold is, separate to the main threshold. Then there's a compiler directives, which lets you look and check whether you're inside the first tier or not. And so the same way we have compiler directives dots in interpreter and in compiled, we have in first tier now as a new predicate. And the Truffle implementation of call targets uses that to add profiling into the machine code to enable going from the first tier to the second tier in order to trigger that second tier compilation. So you could conceivably use that in first tier yourself to do things differently in the first tier to the second tier. I haven't found many opportunities to do yet, but that's an option we could be trying in the future. We could do things differently in the first tier, and we could use left profiling or stuff like that in the first tier. And then what Graal also does is it uses an economy partial evaluation configuration, which uses a different set of optimization passes, and that's why the first tier can produce reasonable code more quickly, and then it has a different configuration for the compiler passes it runs. Compiler thread configurations. This is why I think I skipped a graph here. So we can configure how many compiler threads to use. So -1 is the default since 6 months ago. And -1 picks a good default configuration for how many threads based on the number of runtime processes. 0 doesn't mean no threads, it's the old default. So it means 2 for 4 processors or 1 otherwise, which we found historically was quite a low number of compiler threads to be running. We've already said we experienced quite a high compiler queue. So upping this was important to us. And now we can also set to a specific number, or -1 is now a new configuration that tries to do a better guess rather than 2 or 4. I just skipped I put the graph in by mistake earlier. It's this one. So the old default was to use 2 or 4, and 4 was the right number we found for us, but if you were running on a system with a different number, it wasn't always correct. So running 1 does give a very significant increase on runtime for first iteration. 2 wasn't much different, and then if you increase beyond more that, and this is on a system with around 12 physical hardware threads, there's not much benefit to doing it. When it talks about the number of processors, what it does is it uses available processors, which uses the number of logical processors, which is hardware threads, rather than physical processors. And then if you poke around the code, it tells you the algorithm it uses to work it out. So on my system with 6 cores and 12 threads, that's how we end up with 4 compilation threads. And you can see how it scales to a different number of cores and threads. All this does is it sets the size of the thread pool executor for the compilation jobs being run. You can also look at compile immediately, disabling background compilation, and shutting down threads if they're idle, if you want to experiment with more options for changing the performance of it. Graph caching. So graph caching is an option which is disabled at the moment, but we've experimented with. So there's an encoded graph cache. The default, as I said, is 0. It was added about 10 months ago, and that means it's disabled. During development, you can see the Graal developers experimenting with a default of 512. There's also an unbounded option, or you can set it to anything you'd like. We found that this did have a positive impact on performance. So for it being unbounded, it did fairly well, but it was better off restricting it to that number of 512, which is what they were experimenting with during development. And that did reduce startup and warm-up time. How it does it, compiling and inlining will both use a cache for the encoded graphs. Note that the cache stores encoded graphs, not decoded graphs. So graphs in Graal can exist in two configurations. They can be encoded as a byte array using a packed representation of the graph, and they can be decoded, which means being represented as full Java objects. So with a node object per node. We still need to decode them each time, so they don't come from the cache fully ready to use. I think this is because of the decoding is intertwined with the partial evaluation phase in order to stop very large graphs being produced and stored in memory. Does this mean the cache doesn't do much on the SVM? I'm not sure where the graphs are already available encoded. But this option we did something useful. Oracle haven't enabled it yet. You might want to do an experiment with enabling it on your Truffle languages because it did do something useful for us in the JVM configuration. Queue priority is also something which Oracle seems to be experimenting with. So there's a priority queue true, which is default since about 6 months ago. You can disable it. There's also an option which is the configurable compilation queue. I think this just changes the data structure which is used as the queue. Previously, you could give priority to the low or high tier, which is sort of what this does, but that option was removed. So for us, enabling the queue actually had a negative impact for the moment. What it does is it changes the way that the jobs in the queue are sorted. So by default, jobs are sorted just by the tier. So first tier compilation is always scheduled ahead of low tier, second tier compilation. But if we've enabled the priority queue and we're comparing a job that are both of the same tier and a both of the first tier, then we compare their value, their priority value. And the priority value comes from the number of times that the loop or method was invoked. So the priority comes from the call and loop count. Things which were called more often by the time they get to be queued go first. So I think there's more scope here to experiment with more intelligent ways to queue and sort the priority within the queuing, because this is still fairly simple, but it does have a good impact already. I still think there's lots of different opportunities for doing more for increasing warm-up and startup. I think we need to possibly consider a tier lower than the profiling interpreter. So as we said, Truffle and Graal, Truffle's approach for implementing languages is that there's a single representation for the programs. So that single representation means that profiling and caching are always being done. And we also said that Truffle languages tend to be very aggressive about using profiles and caches, and Truffle would be even more so than other Truffle languages. So that means there's a lot of work being done at that initial interpretation stage. Could we enable profiling and caching after a sort of super low threshold? So you have to be called or run 5 times to enable profiling and caching. Could we enable it based on some heuristics? So if we know from our domain knowledge of our language and our application that some things are very unlikely to be used, could we use that as a heuristic to only, if they're only used once, only don't run them with profiling and caching? But I think that's the sort of thing that I can imagine getting wrong, and using that kind of heuristic and baking it in may find that important code then gets missed. Could it also be enabled based on offline profiling? Could we collect Truffle profiles from an initial run and then use that to inform the next run, profile guided optimization for Truffle languages? Could we look at a bytecode that expands into an AST when it reaches the threshold, so we don't need that full caching profiling AST? Perhaps we should be running a bytecode interpreter for Ruby anyway, in the same way that Espresso uses a bytecode representation, Sulong uses a bytecode representation, rather than having a more traditional AST. Could we have a hybrid bytecode and AST, so that bytecode is run for the first few iterations or is run for slowed paths, whereas the full AST is run by other things? I think possibly need to experiment with this lower tier for interpreting. More intelligent queuing is something I think we need to expand as well. I think that 4,000 long queue is a good sign that the queue is pretty important, and the fact that things can sit in it for 4 seconds is also a good indication that there probably should be lower hanging fruit there to pick out the important things to compile to make an impact more quickly. Can we remove methods that's gone cold since they became hot and got queued? Can we continually sample and reprioritize methods that are hotter now than they were before or colder than they were before? Can we use other heuristics to prioritize? Again, can we use our domain knowledge of the language and the application to design a better queue? And can we plug that in from the application? And again, can we use offline profiling? So using a profile guide optimization and a previous run's information to better inform the next run. Generally, Truffle's philosophy is often handle it all at the runtime based on local profiling information. But we've got tons of domain knowledge about our languages and our applications. And can we use that to build better things rather than treating Start and Warm as a bit of a black box that Truffle has to somehow solve with no information from the application or the language, when we have good information I think we could use? And can we be more aggressively using about that? But there's always corner cases. I think if we try to apply some domain information, we'd probably find that it was often wrong. If we try to do human design heuristics, I think we'll find they're often wrong, and there's actually things that we think should be slow path that are actually quite important to be run. So it's difficult to balance it. I want to make a call for more collaboration. If anyone's got any ideas for a startup and warm up in the Truffle community, then we've certainly got the largest production Ruby application that runs on Truffle, and possibly the largest production application at all that runs on Truffle. And if anyone wants to try any startup or warm-up ideas, we want to collaborate with you, and we can try your ideas, we can try your flags, we can try your compiler changes as well, and we can give you feedback on what they do. And we can do that quite freely and quite easily if you ask us to do that. So I'm calling for more collaboration on that. Thank you very much. Are there any questions?
Okay, maybe I'll go with my question then. So how do you go about finding the parameters that you can tune for instance, like to improve startup time? Is it like something that you do by looking at the implementation, or is there anything that you use to find this kind of information?
We haven't got sophisticated enough yet to be using any kind of automatic search. So we've been trying options individually. We haven't been looking yet at different combinations of options, and then we just try within a range. Usually the results we get for each option are fairly large, and there's a fairly obvious optima within that single option. But yes, I'm curious about the interaction of options. But as other people have said, it's quite combinatorially explosive. You get quite a lot of combination of options quickly. But I want to steer clear of tuning these numbers at this stage, because as I said towards the end, I think there's more opportunity to use intelligence about the application and the language to try and improve these things. And that's the route I'd like to go down. I think there's more opportunity there and more low-hanging fruit. And I think the reason we haven't done that so far is a lot of the philosophy of Truffle has been to let the system handle it automatically. And perhaps we need to back off a bit from that with our philosophical approach to things, and to say instead, actually, let's use some of the knowledge we've got about the application. And it doesn't have to be all done language agnostic, and it doesn't all have to be done without any kind of intelligence about how it works. So that's what I'm keen to try. But if other people are trying stuff, machine learning to automatically scan the option space, then I'm interested in that as well.
Great. Thank you very much, Chris. It's great to have you again this year at the workshop.